is with S. Chaudhary, Anshuman De, Indraneel Haldar, Lavneet Gangal, myself, and Rohan Pujari. Everyone in the author list is in TIFR, split between postdocs and students. And the archive number is 1707.09352. Okay, so this talk is about this very fashionable theory called the SYK theory. Part of my reluctance for giving this talk is I'm not terribly sure myself it's a very interesting theory, but anyway, this is what the talk is about. So the SYK theory is a theory of fermions interacting with random interactions. And what I'm going to be mainly talking about is a variant of the SYK model, so I won't say too much about the SYK theory itself. But the point of the SYK theory is this. It's a bunch of fermions with random interactions. In fact, I think last year at this meeting, Gautam gave a review of this theory. Yeah, and when the number of flavors of these fermions is taken to go to infinity in a certain limit, the interesting thing about this model is that it's solvable. It's solvable at large n. Now, there are many solvable theories. The thing that's special about this theory, the thing that's piqued everyone's interest, at least caught my attention, is that this theory is both solvable as A is solvable, B displays interesting physics. So what interesting physics does it display? The really interesting thing that it displays is that it thermalizes. At times, over times, so of order 1 over the temperature. Okay? This tells you that there is some sense in which thermal physics is strongly interacting. You see, if you have a very free field theory, thermalization takes a long time. Because you've got a bunch of particles in weakly coupled n equals 4 Young mills. The particles have to bang into each other. Each of these bangs takes a long time. So, n equals 4 Young mills at large n, for instance, at weak lambda, would take a very long time to thermalize. A time that goes to infinity as lambda goes to 0. Similarly, vector theories in 3 dimensions, these interesting solvable theories, including these Chern-Simons vector theories, take a very long time to thermalize. So which tells you that there's some sense in which these theories are interacting, but as far as thermal physics goes, they behave almost non-interacting. It often happens that theories that you can actually solve, from the point of view of thermal physics, look non-interacting. This theory is special because it's both solvable as well as has interesting thermal behavior in the sense that thermalizes very fast, times of order 1 over t. There's no small, it's not like times of order t times n, for instance, n to the 1/2 or something like that. Okay? Related to this theory displays the maximum possible value of the Lyapunov index that Surabhi was talking about in the previous talk. The value that you get also from gravity. Okay? So this theory fast thermalization displays chaos, looks like at least its thermal behavior is sort of interesting. Okay. However, there's another reason to be interested in this theory, which I'll review in a minute, but let me say. The other reason to be interested in this theory is that it has been suggested that this theory has a bulk gravity dual description, and that the fast thermalization of this model and this Lyapunov index is an indication that the finite temperature behavior of this bulk gravity dual description is dominated by black hole saddle point. The reason for suspecting this is that black holes have these properties. Black holes have the properties that they display fast thermalization, also saturate this Lyapunov growth. Okay, so this is a really good reason to study. If this is true, it's a really good reason to study the model. Because, you see, as all of us know, there are many puzzling mysteries about black hole physics. And if you could view those mysteries within a theory that was solvable, at large n, and then potentially tractable even at finite n. Because even at finite n, this thing, at least from the point of view of numerics, is just quantum mechanics of a finite number of degrees of freedom. So potentially tractable by some approximation scheme even at finite n, perhaps we could use this model to resolve deep mysteries about black hole physics. So this is the motivation that really piqued my interest. Maybe we can learn about black holes from this model. However, with the SYK, from the point of view of this motivation, the SYK model itself has a bug. And that bug is that the model that is solvable is an average over quantum systems rather than a quantum system by itself. So, while you can think of it as averaging over an ensemble of quantum systems, any point in that ensemble is a quantum theory. It has a spectrum, it has a unitary evolution. Once you average, however, there's no precise sense in which you can associate a spectrum or unitary evolution to this theory. Now, there are many arguments that for many questions, the ensemble average will give you the same as any particular instantiation. But of course, there are small differences, and for some questions, in particular for very late times, the differences may grow large. And we all know that questions involving the puzzles of black hole physics are subtle questions. Suvrat knows that better than most people. And small differences may make a big difference for such a question. So, if our interest in these theories is to try to understand the theories so as to try to resolve deep puzzles over black hole physics, it's a bit worrying that the thing that you can solve is not by itself a unitary theory. And the things that are unitary differ from the things you can solve in some ways. Okay, now maybe you can deal with that. From this point of view, there was an interesting development almost a year ago, maybe about 8 months ago. This development started with Witten and then was carried on by other people. And carried on by other people, namely, in particular, Klebanov and collaborators. And the model I will write down for you in a minute was due to Klebanov and collaborators. And the development went as follows. Consider the following model. Okay, consider psi bar d slash psi. Okay, just del t. It's quantum mechanics. Psi bar dt psi, where psi here is a field that is in some representation of a gauge group. For my context, my gauge group will be On to the power q minus 1. Psi is in the fundamental representation of On to the power q minus 1. Okay? Psi is a field that has indices A1, A2, q minus 1. Okay? Each of these are fundamental indices in On to the power q minus 1. Okay? Psi bar, the complex conjugate of psi, is also in the fundamental of On to the power q minus 1. There are UN versions of these theories, but somehow it will be convenient to deal with the UN. So far I've written down just a free action. But there is a very particular interaction term here. There is a very particular interaction term here with the parameter j times some power of n. Q minus 3? Yeah, okay, n to well, okay, I'll write what's in my notes, which is a bit different, but yeah, right. I get n to the power q minus 1 to q minus 2 by 2. Maybe, yeah. Okay, some power of n, okay. N to the power q minus 1 to q minus 2 by 2. Okay, and this power of n is taken so that it'll have a good large n limit. So this is an effective coupling constant here. Okay, and if you take this theory, and I'm telling you what this psi to the power q means. Maybe I'll just, okay, let me make the statement, then I'll tell you what psi to the power q means. That psi to the power q is a particular index contraction of q size. Okay, and if you take this theory and you look at the, okay, and there's a gauge field here. There are gauge fields for the gauge group On to the power q minus 1, except that we're in one dimension. So one-dimensional gauge fields do almost nothing. Okay, we can work in the gauge at 0 temperature, we could work in the gauge A0 equals 0. And then they're really doing basically nothing. Okay, so there's a gauge field, this is the gauge model with some gauge group. In the appropriate gauge is doing basically nothing. The claim is that the large N solution is the same as the large N solution of the original SYK theory. Okay? In fundamental of each of the ONs. Okay, so each of these is a fundamental representation. A1, A2 is of okay. The claim is that if you take the large N limit of this theory, this large N solution of the theory, and we'll understand this a little better as we go along, it's the same as the large N solution for the SYK theory. In particular, many of the good things about the SYK theory, namely that the theory thermalizes, is true of this theory as well. In a self-thermalizes in a computable manner, this is true of this theory as well. But this theory is an advantage. This theory is an indisputably good quantum system. It's a good quantum mechanics system, unitary, blah, blah, blah. Okay, so this theory here looks like it doesn't suffer from the disadvantage of the SY model that we talked about. Okay, so it looks like an interesting question to understand, to try to analyze the thermal behavior of this model. Perhaps there'll be a payoff. Perhaps we can do what Suvrat wants to do, namely to understand all the mysteries of black hole physics. Okay, now. In this talk, what I'm going to do is the following. I'm going to try to study the dynamics of this theory, focusing my attention on the aspects of dynamics that differ between this theory and the SYK theory. So the SYK theory, its dynamics has been studied to death by many people, lots known about it. However, this theory seems to be a more plausible candidate for resolving the mysteries of black hole physics. So it seems like an interesting question to ask. Does the dynamics of this differ from that of the SYK model in any significant way? If so, maybe these differences are connected to unitarization of black hole physics. We will have very little concrete to say about that, the unitarization of black hole physics, as you can guess. But that's what we're going to do. Okay, so in order to determine the differences in dynamics, I'm going to very briefly tell you about what is known about the SYK theory itself. Okay, the SYK theory itself also is quantum mechanics of fermions, but with some random interactions. Now, something that has been understood very clearly about the SYK theory is that its physics can be thought of effectively as an energy flow. And one way of understanding it is that the parameter in SYK that mimics this thing here, well, let's just say it in this context. It's very similar in SYK. This J is a parameter of dimension mass. Just because J times dt has to have dimension 0. Okay? So the UV, this theory here, this operator here is dimension 1. It controls the dynamics. And this is a relevant deformation because we've deformed it by dimension 0 operator. Okay? Anytime you deform by a relevant deformation, it does an RG. So you have an RG flow. The interesting thing about this theory is that what I'm saying now is a bit inaccurate, but more or less, morally speaking, you go to an IR fixed point. Now, what is this IR fixed point? The IR fixed point of this theory, this SYK theory, is one in which, interestingly enough, this operator becomes, about this IR fixed point, the marginal operator, controls dynamics. Where this operator becomes an irrelevant deformation around the IR fixed point. Okay? And that's summarized by the statement that psi develops an anomalous dimension. The dimension of psi becomes 1 by q. Psi at dimension 0 about the free fixed point, because dt ate up the dt. About the interacting fixed point develops dimension 1 by q.
Exactly the same as this, right?
Exactly the same as SYK. Right, because large N physics is the same, basically. Okay? Now, this 1 by q means that the operator is marginal, whereas this operator now has dimension 1 plus 2 by q, which is larger than 1, which is the relevance bound in one dimension, and therefore becomes irrelevant.
Then one doesn't depend on the sign of things.
Of the dimension? Well, no, I don't think it depends on the sign of J. Does it? Let me think. Does J have a positivity property? Does J have a positivity property? I don't know. Do you know, Gautam? Does J have to have some positivity property? J squared appears in every calculation. In every answer, everything's a function of J. I don't think J has any sign. Anything I've computed always has J squared.
Schwarz has a linear J.
Has a linear J? Okay, maybe we need a particular sign. I'm not 100% sure of this. Maybe we need this J to have a partition. I'm not sure of the sign. Okay. Coefficient of the Schwarz has a linear J. That's right. Maybe it's a mod J. I'm not sure of the sign. I have to think about it. Okay. Now the interesting thing about this, as we said, is that the IR physics is, for the IR physics, this operator is essentially negligible. Now, what does this mean? This means that if you're interested in deep IR properties, then there's symmetry enhancement in this theory. Any symmetry that is a symmetry of this Lagrangian with this term thrown out is symmetry of the deep IR physics of the theory. But you see, it's already clear by visual inspection that we're going to get lots of symmetries, because our deep IR theory is a theory without derivatives. Which is very weird. Never happens in usual quantum field theory. Somehow it's half consistent, not even completely consistent. This is the statement. You know, the theory doesn't quite make sense all the way down to the IR, and you need some cutoff. Anyway, so it's the theory, it's controlled almost entirely by the symmetries of the theory in the deep IR are controlled by an action without derivatives. This, for the SYK people, this had an immediate consequence. See, the SYK people had I've not written down their actions, very similar. Okay? But they had an action that looks something like this. And they noticed that if you do a diffeomorphism coupled with the weight scaling for psi, a conformal diffeomorphism, okay, this action left invariant. Okay? Therefore, they realized that so now I'm switching now attention to finite temperature physics. Okay, we're looking at finite temperature physics, we're doing in Euclidean space, we've got a thermal circle, and every time I say deep IR, that's the same as going to very low temperatures. Okay, so as a function of beta j, as beta goes to infinity. So what they noticed is that in the deep IR, or equivalently at very low temperatures, an effective conformal invariance in this theory. Okay, there's an effective symmetry of the Euclidean Lagrangian, parameterized by diffeomorphisms of the thermal circle, accompanied by appropriate scalings of psi. Okay, it turned out that if you looked at so there's a symmetry of the action. Okay, so there's a symmetry of the action which was diffuse. Now, it turns out that you can take this theory and, at least in the nearly low temperature limit, in the limit of very low but not exactly zero temperatures, you can solve it in the large n limit. This is the solvability of the theory that I talked about. And I won't tell you too much details in this talk, just the important point. The important point is that you knew the exact this theory. The solution is given in terms of a Green's function and a self-energy function. Details don't matter. The important point is that the exact solution here did not preserve this whole diffeomorphism invariance, only preserved a small subset of it. Preserved an SL2 subset of it. SL2R subset of it. Now, whenever you have a situation in which you've got a UV Lagrangian, or you've got a UV Lagrangian which has a large symmetry group, but the solution of the theory breaks that down, okay, you've got lots of zero modes in your theory. The zero modes are parameterized by the coset, symmetry of the theory modded out by symmetry of vacuum. This is no different. See, so the finite temperature physics here was governed by a saddle point, whose details I'm not telling you about. But the important thing about this is that about this saddle point there were very low energy fluctuations. Okay, these low energy fluctuations were parameterized by diffeomorphisms of the thermal circle, and Maldacena and Kitaev and then Maldacena and Stanford and many other people figured out what the Lagrangian for these diffeomorphisms was. And this Lagrangian for the diffeomorphisms was given by a Schwarzian for the diffeomorphisms. And the Lagrangian was light in the sense that the coefficient for the Lagrangian went like 1 by j. 1 by this j parameter, which was the statement that these were almost zero modes in the strict limit j goes to infinity. Okay, the beta j goes to infinity, that these modes became zero modes.
Compare with n. The coefficient n upon beta j.
That's correct. That's correct. N over beta j. Right. So we're thinking of this like, this n to the power q minus 1. Think of this like Newton's constant. Yeah.
Here, usually n is the largest.
N is always going to be the largest thing in whatever we're talking about. N is overall outside, in units of this n to the power minus beta j, this thing is becoming light. That's right. Okay. Fine. So far everything I've said was just review of more than one year old stuff about the SYK theory. However, now we are working with this model here. Okay? The first question I'm going to ask is, look, general theorems tell us that leading large n behavior of this model is the same as SYK theory. But leading large n behavior only determines the saddle point of the theory. If you want to understand fluctuations around the saddle point, that's subleading in 1 by n behavior. Okay? So it's possible, in fact almost certain, that fluctuations around the saddle point of this model will differ from the fluctuations around the SYK theory. That's possible, but in general not interesting. I mean, why do we care if some subleading stuff differs? It would be interesting only if there was differences in the zero mode sector. If the fluctuations that had zero energy or that were very light differed between this theory and the SYK theory, that would be interesting. I'll give you a concrete interpretation of it in a minute, but first we're going to ask the question, are there additional zero modes in this theory? Okay? In addition to those that were there in the SYK theory. And the answer, if you start thinking about it from the way it's presented, is obvious. We could work with either what's called the global or the gauge theory. Let me stick this talk to the gauge theory. So in the gauge theory, we work in the gauge, A0 is equal to 0. We'll soon generalize as we will need to the gauge A0 is equal to constant. Because we're in a thermal circle, we'll need to turn on, but clarity now, forget that. It's not important for what I'm saying now. Imagine A0 is 0, okay? I'm setting A0 equals 0, and everything I say, I'll work in the gauge A0 is equal to 0. I'll be doing unitary or orthogonal transformations of fermions in a minute. These will not be gauge transformations because I will not simultaneously also be turning on a gauge field. Okay? So, suppose I work in the gauge A0 equals 0, stick to that gauge, and I do psi goes to O psi, where O is a global SON to the power q minus 1 transformation. This is obviously a symmetry of the Lagrangian. Any is global. Okay? Now, however, let us look at O, which is a function of time. Look at this symmetry, this transformation. This is not a symmetry of this Lagrangian, because if we don't turn on A0 also, this term in the Lagrangian violates it. It changes. However, as we've argued in the very low temperature limit, we can forget about this. Symmetries of theory are just governed by this term. Therefore, in the very low temperature limit, O as a function of time, such rotations should also turn out to be symmetries of the Lagrangian. Okay? And therefore, by the same set of logic, the same series, the same rationale that Maldacena and Stanford and Kitaev and friends used, we conclude that we've got q minus 1 into n minus 1 by 2 and 2 zero modes about thermal physics. Okay? Now, in our paper we have a sort of half demonstration, meaning a demonstration making some assumptions, that the dynamics of these modes are controlled by a very interesting Lagrangian. The Lagrangian is n to the power q minus 2 by j integral dt u inverse del tu u inverse o inverse I call it, o inverse del to, o inverse del to and this I'll call OI, sum I is equal to 1 to Q. And a trace. So I is summed over all the various components of the gauge group. The gauge group, remember, is On to the power Q minus 1. This is sum to Q minus 1. This Lagrangian here is simply a sigma mod on the group manifold. Okay? That we have this factor of n to the power Q minus 2 times 1 further because of the trace. Q minus 1. Simply the statement that we're dealing with the theory with n to the power Q minus 1 degree of freedom. Okay? And then you get, in addition, this J downstairs here. Okay. This, by the way, that there are these zero modes was confirmed by a competing paper that came out on the same day, not by coincidence but by coordination, by Klebanov and collaborators, in which they did a different calculation and they also found these zero modes. Okay? Now, they didn't argue through symmetries, they did some ladder diagram calculation. Okay. Fine. Now, what is the point of this? The fact that the zero modes of the theory included the Schwarzian action, diffeomorphisms and the Schwarzian action, has been interpreted by various people, including Spenta and Gautam, as a smoking gun of the fact that there is a dual description of this theory, and this dual description includes in its sector a gravitational field. Okay, this diffeomorphism became boundary, the effective degrees of freedom in a two-dimensional ADS2 kind of gravitational theory. Okay, so the zero modes were the thing that govern the low energy dynamics of this bulk, namely gravity. Now what we've got is plenty of other zero modes. How many other zero modes? Well, the number of additional zero modes is this. Now notice that in our theory, Newton's constant, G goes like 1 to the power, 1 over n to the power Q minus 1. Q is 4 or greater, 4, 6, 8, 10. So this grows like, at minimum, like 1 by n cubed, whereas this here is n squared. Now, you can already see this in the Lagrangian, but if you buy the story that the diffeomorphisms are a sign of the bulk dual, then these additional fields here are very plausibly the sign that inside this ADS2 there are also gauge fields. The gauge fields associated with the On, the power Q minus 1. The strange thing about these gauge fields is that the rank of the gauge fields is not held fixed, cannot be held fixed as you take Newton's constant to 0. In the classical limit, the rank of the gauge field grows without bound. Even though the rank of the gauge field grows without bound, the gauge theory in bulk, which is basically the reflection of this theory on the boundary, remains weakly coupled. Why does it remain weakly coupled? Because the thing that governs the coupling constant of a gauge theory is its Stokes coupling. Okay? And in this case, the Toft coupling is basically one factor of n suppressed from here. Okay? And that remains weakly coupled. I've got some Q minus 2. Yeah, right. Sorry. What? N to the power Q minus 1 is the SYK. N to the power Q minus 1 is the SYK. Always dealing with the N, which is the rank of the gauge field. So if you have one further suppression from this, Q is at minimum 4. So you at least have a 1 over my N, which is 1 over the N to, SYK N to the 1/3 suppression. So the Toft coupling is always small in this theory. Okay, and in the large N limit. However, so the theory remains weakly coupled. However, it's a weakly coupled theory with an infinite number of degrees of freedom as n goes to infinity. This is a weird theory of gravity. It's a weird theory of gravity, and we've seen some things like this before, most notably in Rajesh's. Rajesh and Gabardiel had these very interesting theories, which had basically a very large number of light degrees of freedom in the bulk, number of degrees of freedom that didn't stay finite as C went to infinity. However, the theory remained classical. This is somehow reminiscent of that. There are various other analogies you can draw. But the first lesson we're going to draw from this is that, if I've not messed up, if it's true that this theory has a bulk dual description, and if we should take seriously the statement by many people that the diffeomorphism invariance is a sign that it's gravity in ADS too. If we upgrade our vision to away from the SYK theory to the Witten-Klebanov model, then this gravity has to be enhanced with gauge fields. But the interesting thing about these gauge fields is that it's not like a U SO6. Yeah.
There's the Witten model, right? That is what the co-adjoint orbit method will tell you immediately.
Probably. That's probably right.
The Polyakov gravity came out of the co-adjoint orbit.
That's probably right. That's probably right.
Is there some idea of interaction between these?
Well, certainly there will be some interaction because they'll carry energy somehow. Yeah. So you would have to figure out the details.
Interaction between what?
Between the gauge fields and gravity, basically. Okay. So now, just to be clear about what this implies, if it's taken at face value, there's been a lot of people have talked a lot about this Lyapunov index and how it's actuated in this model. Lyapunov index was purely a consequence of the Schwarzian degree of freedom. Okay? It can be thought of as a consequence of the fact that if you linearize the Schwarzian equations of motion and solve, there's an exponentially growing mode. That's basically the heart of the Lyapunov index. Okay? So, when you get suppose you can compute a typical correlation function, a 4-point out-of-time correlation function, there'll be some number times e to the power, this critical value whose value I won't get right, 2 pi by beta or whatever it is. From this mode. However, our new modes will also contribute. You can linearize these equations of motion, see that things grow fast, at most linearly, because it's just del squared t, roughly speaking, think new one. Okay, so in addition, we will have some other number. These numbers to get straight will be work, but they'll be numbers of order 1. Okay, times n squared. It's really n squared and q. I'm not distinguishing n squared by 2, n squared q minus 1. So let's say t. This is a much faster growth than this, but this guy here has the n square. Okay, so in this theory, before you start, you will eventually be dominated by this exponentially growing mode, but you would have to wait a time t of order log n before the exponent takes over, eventually flooding our new degrees of freedom. So this is just as one illustration of the fact that these new degrees of freedom are not just sitting there, they're doing something. Okay, they delay the onset of this exponential growing behavior. What does this mean from the point of view of bulk black holes, if we're going to speculate? From the point of view of bulk black holes, if we're going to speculate, it means that the black holes take some time to get their black holey act going. You know, things aren't thermalizing as fast as you thought, in some sense. You know, it's taking time for it to start growing exponentially. Okay, I won't say more speculative nonsense than that. Okay, so this is the first part of the talk. Now let's move on to the second part. Any questions or comments about it?
I just want one comment to make about the Q equal to 4k.
Q to what?
The Q equal to 4k, at least we have found that if you diagonalize it, the Hilbert space is actually a non-trivial representation of the symmetry. Which means that all the states, if you construct gauge singlets, you'll have to construct multi-particle states or something like that. Excellent. Actually, this has close connection with the second part of my talk.
So can I assist? Are you saying more on this?
No, go on.
My question is that so this worries me a lot, right? Because this behavior you can think of roughly as the behavior of colliding shock waves. You said two shock waves, and you asked how much that effect is. That effect grows exponentially with the separation you have.
Yes.
But you're saying that effect doesn't even, so at log n, that effect becomes huge for ordinary platforms. Center of mass energy of this collision becomes.
Log n, time log n, you're saying. Yeah, if you wait time log n, yeah.
But here you're saying that effect doesn't even occur till you have a separation.
Well, it's occurring. It's just amped by.
I understand. That's dramatically different behavior.
I agree, it's dramatically different. It's basically the statement that you've got a blow energy theory in which most of the modes are not gravity. There are n square plus 1 modes. N square of them are not gravity. Gravity is doing this.
It almost says there's no horizon, right? Because you would have thought that
Yeah, you take, it's like there's a barrier and you have to tunnel through or something.
No, the horizon is somehow
Yeah, something like that. It makes it, yeah, right. Yeah. I sort of agree with this direction of your comments. This is what it is. Okay. This is first. Now, very fast, in 5 minutes, I'll go through the next part. Okay. The next part is closely connected with what Chetan asked. The next thing about being you see, this theory is a gauge theory, unlike this SYK random disorder stuff. Gauge theories are nice. It's not dirty. Okay, so I thought disorder was dirt. Okay. So you can, what else do gauge theories have that disorder doesn't have? Okay. At finite temperature, gauge theories have one additional degree of freedom. The disorder models, or that you miss by setting A0 equals 0. And that's the holonomy. Okay? So in addition to everything I've said, if we're at finite temperature, there's a holonomy degree of freedom. Now, Witten in his original paper was not blind to this. He noted it and then said, well, look, however, the holonomy is just n squared degrees of freedom. The matter is n to the power minus 1 degrees of freedom. N to the power q minus 1 is larger than n squared, so the large n limit is probably ignorable. Okay? And that's true if you keep your temperature fixed as you take n goes to infinity. However, you see, keeping temperature fixed as taking n to infinity is not the same thing as keeping energy fixed as you take n to infinity. Okay? And so to answer questions about the spectrum of the theory, at finite energies, it turns out that it's not sufficient to keep the temperature fixed as you take n to infinity. And what I'm going to do now is illustrate what I'm saying in a toy model. Okay? The actual theory proves a bit hard to solve. The toy model is simply taking the same theory here and deforming it with a mass. Okay? Now, what have we done by doing this? You see, in the original theory, there was only one coupling constant, this J. J was dimension full. So the only real coupling constant was J in units of energy. Now in our theory, no mode is energy smaller than m. So there is an upper bound to the coupling, namely J divided by m. Okay, so this theory is weakly coupled at all energy scales if J by m is much, much less than. So this is the opposite end of the limit that these guys have been studying. But I'm going to, just as an illustration of what can happen, I'm going to show you what happens in the limit J by m goes much, much less than 1. Okay, just to illustrate what could happen in the really interesting dynamical relation. You see, if we're interested in J by m going much, much less than 1, might as well take the strict limit J by m goes to 0. In this limit, what we've done is something interesting. What we've done is decouple all the dynamics of the matter fields, because matter fields become free. However, all matter fields interact with the holonomy. And these non-interacting matter fields induce interesting dynamics for the holonomy. And this interesting dynamics continues to exist even in this limit, and sort of interesting as I'm going to show you. Okay? So in this limit, all you have to do is to integrate out the fields. By the way, in principle, there is a saddle point equation that does this integration out at all m. It's just a very hard equation to solve it if you weren't able to solve it. In principle, there's some equation you can write down, an integral equation that if you could solves the problem. Anyway, I'm going to just do it in a baby way at weak coupling. Okay. So you can ask, what is the effective action as a function of the holonomy field? And if you just, in the strict large n limit, you just have to integrate all these psi's at one loop. And you get a very simple effective action. The effective action, well, the full partition function of our theory turns out to be dOI, integral of all the holonomies of the various SON factors over Haar measure, exponential of sum over n x to the power n by n factorial trace O1 to the power n, trace O2 to the power n, up to trace On to the power n, and I need minus 1 to the power n plus 1. No. This is now this massive model.
I see.
In massive model, you can never ignore this kinetic term. Okay? So now what we've done is go to a limit where everything else interesting has been thrown away, only the holonomy remains. Okay? The really interesting problem is see how all these interact with each other. We're not able to solve that at the moment. Okay? So, the only degrees of freedom of these holonomies, simple calculation, compute this low energy effect. Action is just exactly this. Thank you. X is equal to e to the power minus beta m. Okay? Now, this, I'm just very briefly going to tell you what we find in analyzing this model. There are 2-3 things that we want to say. The first thing I want to say is the following. You see, this model here has 2 parts. This path integral has 2 parts to it. There's a measure that comes from the Haar measure, which is mathematically e to the power order n square. Spenta knows very well. And there is the action here that has q minus 1 traces, and so is order n to the power q minus 1. Okay? Witten's point was that, well, this is much larger than this. And if this is much larger than this in this model, it's certainly the case that all holonomies get localized to just delta functions. All holonomy matrices identity, it's like the holonomy matrix didn't exist. This was basically Witten's point. However, there is another interesting scaling limit that one can take. And the interesting scaling limit is to take the limit so that this and this become comparable. So we want x to the power n, n to the power q minus 1 become like n square. And a way of doing this is to scale x like 1 over n to the power q minus. In that case, x squared becomes smaller than n square. But there's one term of this limit that becomes comparable to the n square. That's the term with n equals 1. So if we take we scale x goes like alpha, hold alpha fixed, we take n to infinity, then we've got an interesting matrix model. One in which this term and the measure compete with each other. Okay? This is not just an interesting matrix model, it's a model that Spenta solved in his youth. It's called the Gross-Witten-Wadia model, at least in the large and limit it turns into that. Okay? And it's an interesting variation on it. Because you see, take the saddle point equations with respect to the eigenvalues of O1. You get a Gross-Witten-Wadia model for O1, but where the expectation values of O2, O3, O4 are effective coupling constants in that model, and so on. So it's a coupled set of Gross-Witten-Wadia models, which you can just exactly solve. Okay? I basically don't have the time to tell you the details of how you solve it, but you can solve it, and you find, firstly, that all the only consistent solutions to this theory are when the eigenvalue distribution functions of all the O's are the same. There are never solutions in which one has one eigenvalue. You know, where this replica symmetry, roughly speaking, is never broken. Just show that's true. The next thing I can show is that as a function of alpha, solving this coupled set of Gross-Witten-Wadia models amounts to minimizing an effective potential. Okay, and the effective potential is V of u is equal to q minus 1 times f of u minus 2 alpha u to the power q minus 1, where f of u has a discontinuity, is u squared u less than half, and is equal to 1 by 4 minus half log of 2 into 1 minus u for u greater than half. So u, this variable u, lies between 0 and 1. Okay? So the full solution to this theory, you can compute the free energy, the finite temperature behavior of the theory as a function of alpha by just minimizing this potential, and then the final answer is e to the power minus n squared times v of u at the extreme. Okay? Now, good. I'm going to show you. Now, this wheel, how it looks like changes as a function of alpha. When alpha is very small, it behaves like this. There's a discontinuity at half, but nothing really changes. This discontinuity is very minor, third derivative. Okay? It goes like this. This is small alpha. Then as alpha increases, something interesting happens. Nothing much changes here, but in this region you develop an inflection point. As alpha increases further, okay, here, and the inflection point splits up into a maximum minimum. Okay? Then as it increases further, the maximum and minimum further migrate each other. Actually, at some point, the maximum hits this phase transition, this half point. The minimum's here. As it increases still further, we get this goes down, and then there's a phase transition. Is it clear? I've not been very good in my drawings, but it's clear what happens. U is trace of rho divided by n. It's the usual thing. Huh? Okay. Yeah, so U is equal to trace O1 by n, which is the same as trace O2 by n, and so on. Okay, so very quickly, what does this tell us? For a certain range of alphas, there's only one saddle point. That's this guy. Once we go past this alpha, there are now 3 saddle points. That's these guys. Okay? And in the canonical ensemble, you make a phase transition from this guy to this guy as alpha, one alpha reaches a particular value. This guy is the one that will continue to the saddle point everyone loves. Everyone who's analyzing SYK everyone who's analyzing this model by analyzing SYK is working in this saddle point. Continue to very large alpha. This is the saddle point Witten referred to. It's the saddle point in which the holonomies become identity. However, there's always the second saddle point. In fact, there's a third one as well. Okay? These saddle points all exist. So much for the canonical ensemble. So as a function of alpha, one lesson is that as a function of alpha, there's a phase transition, like a Hawking phase transition in this theorem. Alpha runs from 0 to infinity. Okay? However, there's a second thing that's even more interesting. As interesting. What? U is upper limit 1. You can see from this log here. The log blows up at 1. Okay. What? It's cos theta. It's even simpler. You see, U is trace O by n. This trace O cannot be larger than n. So it's just maximum upper limit. Okay. Last thing I'll say. This doesn't stop. You see, where this point? Which one? This point? No. I'll tell you what value it is. It's a very complicated value of alpha. No. It will effectively be alpha. Yeah, goes like log n.
Alpha like log n?
Because. Sorry, you're right. Alpha like n, which is temperature like log n. Yes. Yeah, right. So alpha like n. That would be the limit. So very large values of alpha.
In that case, this theory is exponentially suppressed.
Highly suppressed. Very highly suppressed. But it exists. Which may not be important for unitarization. Just pointing out that the second standpoint, for which there's no analog in the SYK model as far as I can tell. Okay? But now there's one last thing I want to say and then I'll stop. And the last thing is about the microcanonical ensemble. You see, it sometimes happens that phases that never dominate the canonical ensemble nonetheless dominate the microcanonical ensemble. That is, as the dominant contribution, give the dominant contribution of rho as a function of E at some E. And you can see that here, because you see, when this phase dominates, the free energy is 1 or 0. Whereas suddenly it jumps to this. So there's some gap of energy where the canonical ensemble never dominates. What dominates? Well, it's these unstable saddle points. Okay? In particular, this one, big rho. And you can compute do computations which actually give you the same answer. If you compute in the microcanonical ensemble, what is the entropy as a function? The entropy as a function of energy. Okay? What is the entropy as a function of energy from the saddle point? You get some coefficient that I'm not going to bother to write down. E log E. The second thing you can do, this by the way is for E less than n square. As long as E is order n square but less than n square, this is a reliable calculation. So the growth and density of states to energies of order n square is E log. The second calculation you can do. The second calculation is to try to compute what the growth and density states in energies of order 1 is. That is given by looking at fluctuation around this trivial saddle point. And interestingly enough, perhaps it had to be, I don't know why, this also gives you the same number, E log E, with the same coefficient. So the fluctuations here, which are order 1, map to the growth and density of states of this unstable saddle. So this makes it very plausible that this E log E growth is universal for all energies greater than 1 up to n square by 2.
With the same coefficient?
Same coefficient. Yeah, it's quite incredible. I don't really know it. It's something to explain.
S is E.
What? S is E log E. What does this tell us? This tells us that this is like thermal gas phase of the theory. Okay? It tells us the growth in number of singlet states as a function of energy. By the way, this integral over the holonomy is imposing Gauss law. So what I'm doing is counting singlet states. And it tells you that the growth in number of singlet states in this theory grows like e to the power E log E. Now e to the power E is famous. It's called Hagedorn growth. It's what you always see in weakly coupled string theories. E to the power E log E is faster than Hagedorn growth. Now, from one point of view, it's not a surprise. Hagedorn growth is a hallmark of matrix degrees of freedom. You have more indices than matrices, maybe you should see faster growth. That's what we're seeing. So from one point of view, it's not a surprise, but from another point of view, from the point of view of bulk physics, it's really strange. Okay? If you start thinking about it for 5 minutes, you'll find all kinds of things to be worried about with faster than exponential growth. One of which is that you might think that if you light a match, the universe will explode. Think about it. Okay? It's a very strange behavior. Okay? I'm just going to leave it at that. This is the second finding. The last thing I'll say, just one sentence, is that we worried about whether this could be an artifact of being in the exactly m goes to infinity limit. Okay? So in order to deal with that worry, we computed the first corrections to this thing in perturbation theory. It's what, of course, took 9/10 of the time in working out. This kind of stuff takes 2 weeks to do. The perturbation theory is hell on earth. But anyway, you can do it. What's interesting is you can do it reliably. Because we're working at very low temperatures, that's not a given. You have to sum infinite classes of graphs to do it reliably. Okay? We can sum the leading infinite class of graphs and find the first non-trivial reliable correction to the finite temperature free energy. I won't tell you how we did it. It's a paper, or you can ask me about it. But you can do that, and the net result of all of that is like the details change. None of the qualitative things I've told you about, namely A, that there's a Hawking-Page transition, or B, that there is faster than Hagedorn growth change. So it seems to us that at least in the region of perturbation theory, around m is equal to infinity, m equals infinity, everything we're saying is reliable. Now, whether it extends all the way down to m equals 0, God alone knows. But this is just an illustration of kinds of things that can happen, which is different between the SYK theory and this theory. This is, of course, clearly different because it makes crucial use of an element that is in this theory that is not there in the SYK theory, namely the holonomies, namely Gauss's law. Okay, I'll stop here. Thanks a lot. Well, in neither part of my talk, except the interacting corrections to this, did the psi to the power q, the contraction structure, matter at all. Of course, what was very important, the first part of my talk, was that you reached that IR CFT. It's very possible that you change the interaction structure and you don't reach an IR CFT.
So it has been hard to find this melonic dominance in the contraction.
Yes, it's hard to find them.
But this rho part is true.
This is just true. This is just basically a free, yes, independent of the nature of it.
The second one.
Including what?
The value.
Oh, yeah. It is 100. This is basically makes no use, no, just the kinetic term. By the way, something I should have said that I didn't say is that using at least action structure, one of the things we can show is that in this scaling limit, when you include interactions, this part of the effective action is universal. That the dependence of holonomies always is proportional to this. Nothing higher ever contributes, which is sort of interesting and very unusual. Typically, when you start doing perturbation theory in the holonomy effective action, you get proliferation of structures. In this scaling limit, this is the only contraction structure that appears. All that changes is these coefficients. So for that also we use.
But for the J by M perturbation theory?
That's for J by M perturbation theory, for the A for the structure of it, and B for the details of it, that's contraction structure is very important. It's very important that only Melonic is. At least, it could be other things also true, but this is all we looked at.